Hello students, welcome to Sri Jayendra's Rank Zone classes. I am your friend and mentor for coming classes with respect to physics. This is lecture number 3 of moving charges and magnetism. So let's begin with today's class. In today's class we are going to discuss about the Biot-Savart's law and their applications. Now, why do we use Biot-Savart law? Basically, Biot-Savart law gives a relation between the current and the magnetic field. Let's suppose this is one of the conductor and this conductor is carrying current I, and if I choose a certain element of it, it's an dl. So due to this current element, a magnetic field would be there into its around region. Now, what would be the value of this magnetic field? That can be determined. Let's suppose this is the point P where I required a magnetic field. This is the perpendicular distance r from the current element. So, what kind of magnetic field and where will be it? That means the magnitude and direction of magnetic field can be determined using the Biot-Savart law. That is the applications of the Biot-Savart law. So let's just have a look that what Biot-Savart law is given. That according to the Biot-Savart law, the magnitude of the magnetic field dB is directly proportional to the current I and the element length dl. That means dB is directly proportional to the, currently I am talking about the magnitude only. Yes, it directly proportional to the I. It is directly proportional to the dl. Technically it should be said as an ideal. Yes, but it would be the same thing. And this is inversely proportional to the square of the distance r. It's a 1 by r square. Yes, and direction, its direction is the perpendicular to the plane containing dl and r. Yes, its a direction would be perpendicular to the dl and r. So if I combined all these things, if I combined all these parameters in the vector notation, I can write like this, that dB is directly proportional to the IDL. It is IDL cross R divided by R cube. I hope this is clear. So that should be is equals to, if I remove the proportionality symbol, it that can be replaced by a constant value which is of mu naught, by 4 pi multiplied by IDL cross R divided by R cube. So this is equals to mu naught by 4 pi dl cross R. It is something like this. It's an A cross B, which could be written as A B sine theta, that you know. Yes, so from this, dl cross R can be replaced by the dl sine theta and divide by R square. Yes, now what is mu naught by 4 pi? Mu naught by 4 pi, its ratio is 10 to the power minus 7. In real sense, mu naught, it is a constant which value would be equals to 4 pi into 10 to the power minus of 7 SI units. You can determine its units. It's very simple that you understand. Yes, so and mu naught is called as the permeability of free space. I hope this is clear. So dB, if I want it in a vector form, it's a mu naught by 4 pi I dl cross r by r cube. And if I want this in scalar form, then, or if I am interested in the only the magnitude of this, then I can write like this, that dB that should be is equals to mu naught by 4 pi I dl sine theta divided by r square. It is the magnitude of the magnetic field with the help of Biot-Savart law, and the direction is given by the right hand screw rule. What it is and how can we determine it, we will check it in the later session of this class. Yes, so first let's compare similarity and differences between the Biot-Savart law and the Coulomb's law. First thing, Both are the long range fields. Yes, for theoretically they can be applied up to infinite distance, but it is on theoretical basis. Yes. Next, both obey the principle of superpositions. Yes, you understand principle of superposition. Great. Now let's just see the differences. Yes, Coulomb's law and the Biot-Savart law. The electrostatic field is produced by a scalar source, while the magnetic field is always produced by a vector source. The direction of the field is along the position vector. Yes, and in this case the field is perpendicular to the plane containing the position vector and the current element. If you want to see this, then let's assume that this is plus charge q and you require an electric field at this point P. Yes, so if this is plus charge q, then you understand that the due to plus charge, electric field will be radially outward. But this is on the same plane. This is on the same plane as the source is present. It is in the same plane where charge is present. But here it is something like this. It is ideal cross r. Yes, so this is perpendicular. This is perpendicular to the plane containing ideal and position vector. Yes, there is no angle of dependence. Yes, it is simply k q by r square. No sine theta, no cos theta, no tan theta, nothing. Here it is an angle of dependence dB directly proportional to the sine theta. It is the angle between IDL and R. I hope this is clear. Is it clear? Any doubts? Any doubts up till now? Anything? No? Great. Now let's just see the applications of Biot-Savart law. These applications are very important according to the NEET examinations as well as JEE examinations. You cannot find even a single paper in the previous years. Yes, you can take papers of last 15 to 16 years from JEE or from NEET. That means previously it was called as an AIPMT. Yes, where Biot-Savart's law question has not been asked. That means the paper cannot be completed without an examiner is asking for the Biot-Savart's laws application. So this is very important. Please look at this very carefully. So this is first application where we are going to discuss about the magnetic field due to a straight infinite length current element. Yes, for your purpose here I am using the finite length conductor so that we can use from later on the infinite length current element. So look at this, that a current segment is there from A to B, and a current is flowing through this element, and I have taken a certain segment that is of IDL, and due to this current carrying conductor, I want a magnetic field at point P. So what we are supposed to do is that according to the Biot-Savart's law, dB should be is equals to mu naught by 4 pi multiplied by IDL sine alpha by r square, and that we understand that it is perpendicular to the plane. So I have mentioned it by making a cross over there. Yes, it is the magnetic field is inside, it's inside the plane containing IDL and R. Is it clear? So let's just integrate this. This is B is equals to integration of dV, that is equals to mu naught by 4 pi IDL sine alpha by r square, and this is due to wire AB. Now look at this. It's an triangle at this point, and this point. It's an alpha. This is 90, and this angle is theta. So it's an, if I take this, it's a alpha plus 90 plus theta is equals to 180 degree. So alpha could be written as 180 minus 90, which is a 90 minus of theta. So alpha can be replaced by 90 minus theta. So if I replace this sine alpha, which should be a sine of 90 minus theta, which could be written as cos theta. So this B is equals to mu naught by 4 pi I integration of cos theta d theta. Now how should I calculate the theta? So I need to cover a point B to the point A. So if from this point P, if from point P, if I'm looking at the point B, I need to rotate it in the clockwise direction, and angle in clockwise direction is always considered as a negative. So this is of minus of phi 2 to the to this angle, that is of phi 1. So I'm going to integrate this with the help of mu naught I by 4 pi a cos theta d theta, while upper limit will be the phi 1 and lower limit will be the minus of phi 2. So it's an integration of cos theta d theta, and let's just replace the value. If I replace the value, it would be mu naught I by 4 pi a into bracket sin phi 1 plus sin phi 2 inwards. I hope this is clear. So what we understand is, this is just the theoretical session. Yes, you must have covered this. You must have covered this in your theory sessions as well. So what we understand by this, that let's suppose this is a conductor and it is having a current I flowing through it. What do you require? You require a magnetic field at this point P, and it is at a distance r from the current carrying conductor. Now what your first task is, your first task should be that you need to make a line to the end of the conductor from a point where you require magnetic field. So this is first line, first end has covered, and this is the second line, this is the second end has covered. Now let's just give them a name. Let's suppose this is phi 1 and this angle is phi 2. If this has done, you can write like this. It's a B is equals to mu naught I divided by 4 pi a multiplied by sine phi 1 plus sine phi 2. This is just the magnitude. This is just the magnitude according to the Biot-Savart law. Now let's work for the direction of magnetic field. Using right hand palm rule. Yes, you can use right hand palm rule to find out the direction of magnetic field due to this wire. So what you need to do is that thumb of your right hand will point towards direction of current, and stretch your fingers towards a point where magnetic field is required. Now palm of your right hand or palm of your right hand will show the direction of magnetic field. Now try this principle. Try this principle on this situation, that you should arrange your right hand. Please mark my word. You should arrange your right hand so that a thumb of your right hand will showing the direction of the current, and you need to stretch your fingers towards the point. You need to stretch your fingers towards the point. You need to stretch your fingers towards the point where magnetic field is required. So if you can arrange this, then the palm of your right hand will represent the direction of magnetic field. So if I observe this, I find that magnetic field at this point is within, it is an inside the plane. I hope even you got the same answer. Yes, let's try one or two questions according to the direction so that you can have a grip over it. Let's suppose the situation is something like this, that this is current carrying conductor, this is point P, and this is separation R. So currently we are working for the direction only. Yes, so now let's do it. That arrange your right hand on the current carrying conductor such that your thumb will represent the direction of direction of current. Yes, can you do it? Great. Now stretch your fingers of right hand at a point where magnetic field is required. Have you done it? Have you? Have you done it? Great. So now where is the palm? Inside the plane, outside the plane? Where is it? Yes, it is outside the plane. So this is can be represented like this. I hope this is clear. Is it clear? Is it? Great. Ready for one more? Suppose this is something like this, that the separation is R, this current is I. So what you need to do is arrange your right hand on the current carrying conductor such that your thumb will represent the direction of current. Yes, now stretch your hands towards the point where magnetic field is required. Yes, have you did it? Yes, then palm will represent the direction of magnetic field. It is inside the plane. I hope this is clear. Yes, this is the direction of magnetic field. One more. Let's have a look. This is point P. This is separation R. This is separation R. Now, how can you do this? How can you do this? Arrange your right hand. Arrange your right hand in the direction of the current carrying conductor. Yes, first task has been done. Now, stretch your fingers. Stretch your fingers towards the point where magnetic field is required. So, now, again, this is downward direction or inside direction. Sorry. So, this is the direction of magnetic field according to the right hand palm rule. Yes, you can use another shortcut. Basically, this is not a trick. This is no logic behind it. It's a short trick only. So, how can you use this? Let's understood it. That always imagine your conductor as a circular loop that will include a point where magnetic field is required. So first task, you need to do this. You need to imagine your conductor as a circular loop, and that circle should be made such that a point where magnetic field is required should be covered. Now, if current is in clockwise, magnetic field will be, if current is in clockwise, magnetic field will be inside the plane, and if current is anti-clockwise, if current is anti-clockwise, magnetic field will be magnetic field will be outside. Yes. So even you can use this. Now, how can I do this? Go through the short trick first. Go for twice and very carefully that you need to imagine your straight conductor. You need to imagine your straight conductor as a circular loop, and this circular loop should include a point where magnetic field is required. Now, if current is flowing through this imaginary circular loop in clockwise direction, then the magnetic field will be inside the plane, can be represented by cross, and if current is in anti-clockwise direction, magnetic field will be outside the plane, again perpendicular and outside the plane. So this can be worked like this. Let's suppose this is the conductor and this is a point and this is the separation R. So what you need to imagine is that this is circular loop, something like this. I'm going to bend this conductor such as this is I and this is point P. It does not require that it should be a center only. Yes, because this is just an imaginary loop. Yes, so if you imagine this in this, look at this, a direction of current should be the same because only the direction of current will represent the direction of magnetic. So if I observe this carefully, I can understood that this is the for the circular imaginary curve, the current is moving in the clockwise direction, and if current is moving in clockwise direction, magnetic field will be inside the plane. Now, one of the mistake that you can commit over here is that let's suppose you have made a circle over here. That, sir, can I make it something like this? Because it is the same thing. But in this situation, your point P will be on this direction. And this circle, it is definitely a circle, but this circle is not covering a point where magnetic field is required. Look at this statement again, that always imagine your conductor as a circular loop that will include a point where magnetic field is required. Yes, so in this mistake you are not including a point where magnetic field is required. So this is absolutely incorrect and you are not, or you should not make this mistake. I hope this is clear. Is it clear? Great. So shall I practice it? Let's have a look. Suppose this is the conductor and this is the point where magnetic field is required. So what you are supposed to do is that bend this something like this. Yes, so current will be moving in this direction. Is it clockwise, anti-clockwise? Yes, it is clockwise. So magnetic field will be inside the plane. That's it. You did it. Great job. Yes. Let's say suppose a two conductor is there and you require a magnetic field over this point. Two conductors are there and you require a magnetic field at this point. How could you do this? How could you do this? Yes, as you can see, this is moving in the clockwise direction. So this is imaginary curve. A current is moving in the clockwise. Magnetic field should be inside the plane. That's it. I hope this is clear. Is it clear? Perfectly sure. Great. Now let's work for the magnitude and direction both. So first, let's find out a magnetic field due to straight infinite length conductor. Let's suppose this is a straight conductor which has been extended up to infinite, and due to this conductor a magnetic field is required at point P, and this point P is at a separation of R. So what is my first task? What is my first task? First task is to, where magnetic field is required, start a line from there on the end of a conductor. So if I observe this, let's suppose this is the end of the conductor, so I will assume this is theta 1, but you will say, sir, that is not the end of the conductor, it has been extended to an infinite. So I will increase my angle something like this, and this angle has been increasing. If you observe this carefully, theta 2. Even you says, no sir, this is not the end, it has been go beyond this. So if I want to reach to the infinite, I need to make a straight line over here. I hope you understand. And that angle will be the 90 degree. I hope you understand this. Even on this side the angle will be 90 degree. Yes, so this two angle, that means my alpha beta, or you say phi 1 phi 2, both, let's say it's an alpha is equals to 90 degree, it's a beta is equals to 90 degree. Let's say this as an alpha and this as an beta. Yes, so this both alpha beta both are 90 degree. According to the Biot-Savart law, this should be mu naught I divided by 4 pi r multiplied by sine 90 plus sine 90. This is 1 plus 1 2, and that could be written as mu naught I by 4 pi r multiplied by 1 plus 1, that is of 2, that should be is equals to mu naught I by 2 pi r. Yes, and what is the direction? So let's just bend this. If I bend this, it is something like this. Yes, current is moving in the clockwise direction, and if current is moving in the clockwise direction, magnetic field will be inside the plane. I hope this is clear. Is it clear? Is it clear? So very important point. First, when any section is extended over infinite, angle on that section will be always 90 degree. Now every time we are not going to discuss that this is theta 1 and this is theta 2 and that has to be has to be extended and something like this. No, we are just going to do this at every time, that when any of the section, y section I have written because there are conductors which are semi-infinite. Yes, we will see this. But if on this point, this is my first section, this is my second section, as my first section has been extended over infinite, I have written it as an alpha is equals to 90. Even my second section has been extended over infinite, so I have written it as a 90 degree again. So it's a 90 and things will be done. I hope those things are clear. Yes, so when any section is extended over infinite, angle on that section will be always 90 degree. Yes, first key point. Now let's look at the second key point. Let's assume that your current carrying conductor is something like this, and you require a magnetic field at this point, and the separation is R. So if you observe this, that if you extend this length element, it is at the same point, it is going to meet at that point where magnetic field is required. Now what is Biot-Savart law? It is mu naught by 4 pi I dl sine theta by r square. In this case theta is equals to 0 degree and magnetic field will be 0. So the conclusion is when magnetic field is required, due to straight conductor at a point where theta is equals to 0 degree. B, that means magnetic field will be always 0. This could be represent something like this, that let's suppose this is the current carrying conductor and you require magnetic field at this. So this is first case. It could be even represented like this, that this is current carrying conductor and at this point you require a magnetic field. Let's say this is current carrying conductor and at this point magnetic field is required. So what you need to do is you just extend those points. If they are going to meet it, that means magnetic field will be 0. Look at this. Yes, if it has been extended on a backward side. Fourth, let's suppose yes, and at this point this is I. So let's just extend it. Yes, so this will make a 0. This will make a magnetic field as a 0. It is something like this. So this all cases and every cases will make a 0 magnetic field. I hope these things are clear. Is it clear? Is it? So now let's work for the magnetic field. Find magnetic field at point P. It is something like this. This section is extended over infinite and this section has been terminated over here, and this is the point where magnetic field is required. The current flowing is R. The separation from current flowing, that means current carrying conductor to the point, is R. This is called as the semi-infinite wire. This is semi-infinite wire. So how could I do this? So what I understood is that this is alpha, this is beta. As this has been extended over infinite, this should be 90 degree. Now what I need to do is I need to make a one line that covers the end point of the wire, but here it is the end only. So if I make a line over here, this will make a 0 degree. So now I am having an alpha, I am having an beta. So let's just find out the value using Biot-Savart law. It's a mu naught I divided by 4 pi r multiplied by sine of alpha plus sine of beta. So that should be is equals to mu naught I divided by 4 pi r multiplied by sine 90 degree plus sine beta, it's a 0 degree. So this is sine 90, which should be a 1, which should be mu naught I by 4 pi r multiplied by 1, and sine 0 has been gone. Now where it would be? Inside the plane, outside the plane? Yes, absolutely, it is inside the plane. That's it, you did it. Great job. I hope this is clear. Is it? Well done. Next, so have your pen and paper ready. Now you understand where is the magnetic field and what should be its value. So keep your pen and paper ready and do it with me. Find out magnetic field at point P. In this situation, this is a finite conductor having length 2L. This is a finite conductor having length 2L. This is point P and this length is L. You require magnetic field at this point P. So what you need to do is that connect connect the ends of the wires from point P. So this is first end, this should be second end. Make this angle as an alpha, make this angle as a beta. So what I understand is that this is midpoint. That means this length must be L. Even this length must be L. And this length is L. So this alpha would be a 45 degree and this beta should be of 45 degree. So alpha and beta has been written and that would be equals to 45 45. So magnetic field B could be written as, it's a mu naught I by 4 pi, the separation is L, into sine alpha plus sine beta. Yes, so this is equals to mu naught I divided by 4 pi L multiplied by sine 45. It's a 1 by root 2 plus sine beta, it's a 1 by root 2 again. So this is equals to mu naught I by 4 pi L multiplied by 1 by root 2 plus 1 by root 2. It's a 2 by root 2. That should be is equals to mu naught I by 4 pi L multiplied by, this is 2, this is root 2, this should be root 2. So this is mu naught I by 2, this is 4, this is root 2, so this is 2 root 2. That should be 2 root 2 pi into L. That's it. You did it. Great job. Yes. Now work for the direction. Look at this. A current is flowing in this direction. So if I bend this, it will be something like this. As it is moving in the clockwise direction, so imaginary current and imaginary loop is moving in the clockwise direction. Magnetic field will be inside the plane. Is it clear? Is it something like this? So can you do this? Is it possible? Can you? Are you sure? Okay, great. Let's work for the next question. Do it quickly. A clock is running high. Yes. And time is going. So please do very very fast. Find out magnetic field at point P. Suppose you require a magnetic field at this point. Let's say on this point. This is a length of 2L. Even this is length of 2L. So this separation is 2L from here. And this separation is 2L from here. So you require a magnetic field at point P. So what you need to do is that when more than one segments are there, always give them a name. That this should be my first segment and this should be my second segment. Now work for the magnetic field for each segment. So first let us consider only the first segment. So what you need to do, follow the basics, that from point P make a line on the ends of the conductor. So this is the end of the conductor and you are going to make a line over here. Yes, this angle, look at this, this is 2L, this is 2L, so this must be 45 degree. And the another angle should be something like this. So it is an alpha equals to 0 and beta is equals to 45 degree. This is the first scenario. Now let's work for the second angle, that this is 2L. So what you need to do is you need to again make a straight line over the ends of the conductor. This is the end of the conductor number 2 and this angle is 45 degree, and this angle, this is alpha is equals to 0 degree. This could be written as beta. Yes, here alpha and beta both are positive. So there is no confusion between them, then which one is to be taken as an alpha and which one is to be taken in a beta in most of the cases, in almost more than 90% of cases. So let's just work for it. Now just find out the magnetic field due to 1. It's a B1 which should be equals to mu naught I divided by 4 pi into separation, which is a 2L, multiplied by sine of 45 degree plus sine of 0 degree. So this is equals to mu naught I divided by 4 to the 8 pi L into bracket sine 45, which is equals to 1 by root 2. This is B1. Now let's just work for the B2. What is it? It's a mu naught I divided by 4 pi multiplied by the separation, it's a 2L, multiplied by sine of it's a 45 degree plus sine of 0 degree. Yes, so this is mu naught I divided by 8 pi L multiplied by sine 45, it's a 1 by root 2, and sine 0 has been vanished as it is a 0 itself. Now as this wire, wire number 1, is converted to a circular loop and point P could be there, and so that the magnetic field would be in the inside the plane. So if it is inside the plane, this would be inside the plane. For the second case, this wire, so look something like this. This is, yes, so this point P, for this segment, it is something like this. Yes, it is clockwise, so B1 is inside the plane. Now what about second? The current is flowing like this, so it should be an anti-clockwise, whatever the direction of current that has been mentioned. Yes, so it is anti-clockwise, and as it is anti-clockwise, it is outside the plane. So this B net could be written as B1 minus of B2, and as both are having same magnitude, mu naught I by 8 pi L into 1 by root, the B net at point P would be the 0. That's it. I hope these things are clear. So what you need to do is keep things very very simple. Always work for the one-on-one basis, that when more than one segments are there and you need to find out the magnetic field due to this segments, what you need to do is you need to simply make one-on-one basis. Yes, take any one conductor, find out magnetic field for first work for the magnitude, and then go with for the direction, then work for the second conductor, find out its magnitude, and then work for its direction. At last, if both are having a magnetic field in the same direction, you are going to add it, and if both are having a magnetic field in the opposite direction, you are going to subtract it. It is as simple as that. I hope these things are clear. Is it clear? Is it? So can you do this? Very very easy. Yes, can you do this? Are you sure? Great. Let's work for the next question. So the next question is, let's suppose a square is there, something like this, and in that current is moving like this. The square is having a length of 2L by 2L. At a midpoint, a point P is there. Your requirement is find magnetic field at point P. The current flowing is I. Yes, so same current is flowing because it is a single wire, it's a single frame only. Yes, so what you need to do is you need to understand each one. Yes, it's a first, this is second, this is third, this is fourth. Let's work for the first. This is the midpoint, so this length should be the L. Now let's make a line on the endpoints. So for the endpoints, this would be the angle. Yes, the complete length is of 12, so half of the length is L. This is 45 degree. Again make a line on this point. Yes, again this is 45 degree. So the situation is B1 should be is equals to mu naught I divide by 4 pi L into bracket sine 45 degree plus sine 45 degree. I hope this is clear. So that should be is equals to mu naught I by 4 pi L into sine 45 1 by root 2, again sine 45 1 by root 2, this is 2 by root 2. Yes, so keep this. Now let's work for the second, and you can also find out the direction of it. First, direction of it, as it is moving in clockwise direction, the direction of magnetic field will be in the inside the plane. So work for the second. If I work for the second, this is L. If I make two lines, something like this would be 45 degree. Again, this would be the 45 degree. If I work for the third segment, it would be the same situation. Even this would be the 45 and this would be the 45. So I understand that magnitude wise, B1, B2, B3 and B4 will be the similar. Now let's work for the direction wise. Yes, as you can see, this point P, is there. For every conductor, current is flowing through clockwise direction because direction of current is same through everyone. So everyone is having a magnetic field which is inside the plane, something like this, inside. Yes, so this B net would be equals to 4 times of B1. Yes, so this is 4 multiplied by mu naught I divided by 4 pi L multiplied by 2 by root 2. So this 4 and 4 has gone. This is 2, this is root 2. So this is root 2 times of mu naught I divided by pi into L inside the plane of the frame. Yes, I hope this is clear. Is it clear? Any doubts? Is there anything? Any doubts? Any concern? Anything? Are you sure? Great. So now let's work for the second. Let's suppose this is equilateral triangle. A length 12. As I said, equilateral. Angle would be 60. So even the length would be the similar. It's a 12. You require magnetic field at this point P. So this length will be the L. Even this length will be L. Find magnetic field at point P. Current is moving in this direction. Yes, in anti-clockwise direction for everyone. If it is moving in anti-clockwise direction for everyone, that means for each one direction of the magnetic field will be the same. Now let's work for the magnitude. So what I need to do is, now always look very careful that from point P you are going to make an angle. Students generally make a mistake that they are going to use this angle. No, this is not the angle that I need to put as in sine alpha or sine beta. What you need to do is you need to just connect these two points and make an angle over here. This could be your alpha. Same way connect this line over here and this would be your angle. This is beta. So this is 90 degree. Yes, that I understand. As this is this complete as a 60 degree. So half of the angle, it's a 30 degree. So this is 90, this is 30, 120. So alpha would be equals to 60 degree. Same way here, this is 90, this would be 30. 90 plus 30, 120. So beta would be equals to 60 degree. So now let's work for it. Find out the magnetic field due to any one of the wire, and then we will multiply it. Then we will multiply it by 3. It's a B1 that should be equals to mu naught I divide by 4 pi multiplied by this distance. Now what is it? Let's assume it that it is a x distance. It's a mu naught I by 4 pi x multiplied by sine 60 plus sine 60. So that should be is equals to mu naught I by 4 pi x into 2 into sine 60. Sine 60 would be a root 3 by 2, so that should be mu naught I by 4 pi x multiplied by this 2 has gone, and this is of root 3. As this is moving in anti-clockwise direction, magnetic field will be outside the plane, but this is not the final. Yes, I'm going to work for the B net, but before we go to it, let's just find out the x. So for the x, you need to understand that this is the situation. This is the 30 degree. This is the x which you are looking for, and this is the length L. So what you can do is tan 30 degree should be is equals to x by L. So this x equals to L multiplied by tan 30. And what is tan 30? It's a 1 by root 3. So this is x. So let's just replace the value. It's a mu naught I divided by 4 pi multiplied by x. X is the L by root 3 multiplied by this is the root 3. So this is equals to 3 mu naught I by 4 pi L. And B net will be equals to 3 times of B1. It's a 3 3s are 9. Mu naught I by 4 pi L. That's it. Where is it? Yes, outside the plane of the conductor. I hope this is clear. Is it clear? Is it? So can you do this kind of questions? Can you? Are you sure? Can it be done? Can it be? Great. Let's work for the next question. That the situation is something like this. Let's say from 2I current has entered and 2I current has left. This is a point P, and this is a square of length L. Yes, so your requirement is find out magnetic field at point P. This is the requirement. Find out magnetic field at point P. How could you do this? How could you? What could be done? What could be done? You need to find out magnetic field at point P. So what you must do is that first understand that this is the 2I current that is entering the circuit, and this is the 2I current that is leaving the circuit, and this is a square frame and nothing has been given. That means I can understand that this is a uniform resistance wire. That means resistance of this wire and resistance of this wire as well as resistance of this wires would be the equal. So if certain current is flowing in this direction and the another certain is flowing in this direction, they will be distributed equally, because if you look at this loop, it is having a resistance of 2R. Even if you look at this loop, it is having a resistance of 2R. So the current will be distributed uniformly. So here from this section current I would be going, and from this section current I would be going. Now what is the magnitude of this currents? Let's have a look. To find out the magnitude, understood that this is the situation, and for them this is the point P. As it is a midpoint, this is length L, so this length should be L by 2. Even this length should be L by 2. You need to make a line over here. This would be 2 lines. Even same is here. Yes, so if this is L by 2, even this is L by 2, this is L by 2. So every angle alpha and beta would be a 45 degree. This is current flowing through this, and it is moving in clockwise direction. This is point P. So as it is moving in clockwise direction, magnetic field is inside the plane. So B, a magnetic field, should be is equals to mu naught I by 4 pi into bracket L by 2 into bracket sine 45 plus sine 45. It's a 1 by root 2 plus 1 by root 2. This is 2 by root 2 multiplied by 2 times, and this is inside the plane. A same case, this is the first segment. A same case could be considered like this. Yes, it is the point P. This length will be L by 2. This length will be L by 2. If I make an angle over here, this should be and this should be 45 45. This should be and this should be the 45 45. So I understand that magnetic field of first segment and magnetic field of second segment, it is same as the B1, but this magnetic field at this point P, this magnetic field P is outside the plane. Why? Because here the current is flowing in an anti-clockwise direction. So this B net would be equals to B1 minus of B2, and that would be equals to 0. I hope these things are clear. Is it clear? Is it clear? Are you sure? Do you understand this? Any doubts? Any doubts on this? No? Okay. So ready for the one more question. Same kind of questions. That let's suppose a square frame is there, and let's suppose 4I current is entering over here, and 4I current has been leaving the circuit from here. This is a point where magnetic field is required. This length is 12. You have been given that find out magnetic field at point P. This is the requirement, find out magnetic field at point P. And while you are going to find out the magnetic field, understood that this is a square frame made up from a uniformly distributed resistance wire. That means resistance of each segment, that means each 12 length of wire would be the same. I hope this is clear. Yes, so take your time of 30 seconds and think that how should I do it. First you need to consider that whether my resistance of wires, that means because the 4I current is needed to be distributed into two segments, because there are parallel segments would be there. So does both the sections having same resistance? If it is having same resistance, then current distributed would be equal, as it was the case of the previous question. Is it same in this case too? Is it? Think over it and let me know what can we do, or What should we do? What should we do? How could I do this? What is your idea? Yes? What do you think? What do you think? What can be done? Yes, any idea? Any idea? Anything? No? Let me help you. Let's suppose, consider that resistance of each segment. This is R, this is R, this is R, and this is R. So, so a current should be distributed from this point because it is having a two option. One of them would be going through this, one of them would be going through this. Whatever the current that has been going through this has to pass through this 3R resistance. So it is something like this. This is 3R, and here the resistance is R. So here 4I current has entered the circuit, and from here a 4I will be leaving. So what I need to understand is that this is the 4I current that needs to be distributed in this two parallel wires. That means the parallel resistance. Yes. So, and both these resistors are different. A 3R resistance will be having a lesser current because we always know that current will always prefer a path having lower resistance. So a total current should be divided into 4 segments, from which 3 segments will be going through this and one of the segment will be going through this. If you want to check it, or if you want to verify it, then you can understand that, find out the potential of this. It is V1 is equals to I into 3R, and find out the potential drop across this. It's a V2 is equals to 3I into R. Look at this. This V1 and this V2 both are same. That means yes, I have distributed it perfectly. So current I has been passed through this, and current of 3I has been passed through this. I hope this is clear. Now what you need to do, you need to just focus. You need to just focus on the magnitude of the magnetic field. So let's understand this. This is my first segment, this is my second segment. Let's work for the first. It's how should I do this? This should be length L, this should be 45, this should be 45. So let's just quickly do it. It's a mu naught I divided by 4 pi L multiplied by sine 45 plus sine 45. It's a 1 by root 2 plus 1 by root 2. Yes, and this is for the one wire only. So for this three wires, that should be multiplied by 3. So this is equals to mu naught I by 4 pi L multiplied by 1 by root 2, 1 by root 2. It's a 2 by root 2, and this is 2 3s are 6 by root 2. Keep it as it is. Yes, and as current is moving in the clockwise direction, what I need to do is, this should be inside the plane. This is mu naught I by 4 pi L multiplied by 6 by root 2. I hope this is clear. Is it clear? Is it? Great. Now let's work for the second wire, second segment. That means it's a B2, that should be is equals to, again do the same thing. This should be 45 and this should be 45. So this is equals to mu naught I by 4 pi L, mu naught I by 4 pi L multiplied by 1 by root 2 plus 1 by root 2. But this I should be represented as I dash because total 3I current would be going. So that should be is equals to mu naught multiplied by 3I divided by 4 pi L multiplied by 1 by root 2 plus 1 by root 2. This is 2 by root 2. So on a totality, it's a mu naught I by 4 pi L multiplied by 6 by root 2, and this is moving in the anti-clockwise direction. So this is on the outside the plane. So this is B1, this is B2. Now look at both the magnitude very carefully. Do you find it equal? Do you? Great. Second thing, both are having an opposite direction. Yes, so as both are same in magnitude, both are same in magnitude, but both are opposite in direction. So this B net could be written as B1 minus B2, and that would be equals to 0 because both are same in magnitude. So is it clear? Is it clear? Are you sure? Are you sure? So let's summarize this. Let's summarize this. This is very easy. That when certain current enters the circuit and if same current is leaving the circuit, and if you extend the entering current to a point where magnetic field is required, and it makes theta is equals to 0 degree, then it will be always having always having zero magnetic field. I'm talking about the net magnetic field. So let's just observe this both the numericals one more time. In first numerical, this was the situation that certain current was entering, certain current was leaving, and you want a magnetic field at point P. So what you understand is that let's just extend it. Yes, it is going to meet at here. So it means B net must be 0. Now in the second situation, the circuit was something like this. You require a point P here, that certain current entering and certain current, a same current is leaving. That means I current has been entered and I has been leaving. So let's just try to extend it. This is entering. Yes, again in this case B net must be equals to 0. So no need to calculate it, that what amount of current is flowing and what amount of current is leaving and everything. That every stuff, yes, you must understand this. But always understood that I am not saying that when and when square is there magnetic field is 0. No, I am not saying this. Let's suppose this is the situation. In this situation, current is residing within the circuit. It is not entering, not leaving. It is flowing within the circuit itself. So this is the case where B net could not be equals to 0 and it would be a certain finite value. I hope this is clear. I hope this is clear. Is it? Is it clear? Great. So let's just wind it up this session over here. We are going to do certain numericals based on this topic only. It's a magnetic field due to straight conducting wires. Yes, but before you tune up to that, please revise this session. What I want is that when you tune to the second session, you must be through with the each and every tricks and each and every concept behind it. So please try to solve at least 30 to 40 questions and tune in to the second lecture of the same session. Yes, thank you. Have a good day. Take care. Bye bye.